In this lesson, we're going to review functions and their graphs. So let's first review the definition of what a function is. So if we're given two sets of numbers, x and y, a function, denoted by f of x, is a correspondence that assigns to each number x in the set x a single number y in the set y, and we use the notation y equals f of x to denote that correspondence. Or, like this, we say the number x is mapped to the number y. That's what that little arrow notation means. So for example, you've been dealing with functions for a long time now. Whenever you're given an equation like y equals x squared, this defines y as a function of x. Since for any number x that you're given, you just take that number, put it in the equation here for x, and then you get back a number y. So for example, if x is 2, you put 2 in here for x, and you get back that y equals 4. 2 squared, and that is 4. So in other words, 2 is mapped to 4 under this function, or we can say the point 2, 4 is on the graph of this equation y equals x squared. Now, to indicate that this is a function, we can use function notation, as we'll mention soon. We can also write, instead of y equals x squared, to indicate that y is a function of x, we can say let's let y equal f of x, and so this is equal to x squared. And notice then, if we put the number 2 in for x, we get f of 2 equals 2 squared, or 4. So this is called function notation when we do this. And down here we have the graph of what the function x squared looks like. So you should have seen this before. This is the graph of a simple parabola, we call it. That curve right there is our graph of y equals x squared. Notice that we've found out that if we put 2 in here for x, we get 4 back for y, and so the point 2, 4 should be on the graph of this curve. And notice if we keep track of this point right here as we move it along the curve, you'll see the point 2, 4 appear. So notice right here, when x is equal to 2, notice how when x is equal to 2 right here, y is equal to 4. So 2 gets mapped to 4 under this particular function, y equals x squared. Similarly, if we put 3 in for x, we would get that 3, 9. 9 is equal to 3 squared should also be on the graph of this curve, and that was the point that we had up here a second ago before I moved the slider bar. Right there is 3 on the x-axis and 9 on the y-axis. Now there's another important thing to note here. If you look back up at our definition, we use this terminology, a single number y. If we put a number for x into our equation, we should only get a single number back for y. So what that means is that the graph of our function has to satisfy what we call a vertical line test. So if I draw any vertical line through the graph of the function, it only intersects at one point right there. So in other words, for each x value, what that's telling you is that for each x value, you will only get back one y value. And so when your graph satisfies this vertical line test, that's when you have a function. So here's our function notation that we mentioned a second ago. So we will write f of x equals x squared to indicate that y is a function of x, meaning that if we put one number in for x, we only get back one number for y, one and only one number, and that's the same as saying the graph of our function satisfies a vertical line test. Every vertical line only hits the graph at one location. Now, to become a little more familiar with this function notation, suppose we're given this function f of x equals x squared plus 2x plus 1. Let's evaluate the following quantities here. So what would f of 2 be? Well, anytime you're dealing with function notation, if you're given a function like this, no matter what's inside the parentheses, even if it's anything like a box, anything inside the parentheses gets placed in for each x that is appearing in your function definition. So for example, in this case, f of a box would be the box squared plus 2 times the box plus 1. And it doesn't matter what's inside those parentheses. So what would f of 2 equal? Well, f of 2, you put the 2 in place of each x. 2 is like the box here. And so of course that's going to be 2 squared. And that is 4 plus 1, or 9. So in other words, under this function, 2 is mapped to 9, or 2 comma 9 would be on the graph of your function. That point would be on the graph of your function. Now what would f of t be? Well, f of t, whatever's inside the parentheses goes in place of the x. So this would be t squared. I replace the x with the t. And there we go. That's all it is. It just looks like we just changed the letter x to a t, and that's exactly what we did. That's all we did. Now here's one where people tend to make a common mistake. What is f of x plus h? This sometimes trips people up. Well, f of x plus h, now remember, don't get confused that there is an x here and an x here. Whatever is inside the parentheses here gets placed in for each x up here. So in this case, we simply put x plus h in place of each x up here. And what we end up with is and there we go. That's all you have to do. You just put whatever is inside the parentheses in place of the x. It doesn't matter if you have x's down here. Now the common mistake that people make oftentimes is to write this, and this is an error here, so don't do this, is to write f of x plus h. I'm not going to put an equals here, so you don't think it's equal to this. A lot of times people will say that this is x squared plus 2x plus 1 plus h, and then they'll add the h on the end. Well, that's not correct. You need to put the x plus h in place of each x here. You see, this here is certainly different from this up here. What you've actually written here is this is actually equal to f of x and then plus h on the outside of the parentheses. That's actually what we have here, because you see this term right here, here's your f of x, and then you're just adding h on the end. Well, that's exactly the same as doing this right here. So do not make this mistake of writing f of x plus h as being f of x plus h like this. So don't make that mistake. These are two different things. Now let's evaluate f of x plus h minus f of x over h. So this quantity Alright, so first of all, the f of x plus h. Well, that's going to be okay, so there is f of x plus h. Now minus f of x. And then we divide by h. And there we go. Now there's our answer, but let's actually simplify this. See if we can cancel that h in the denominator. So this actually simplifies as follows. So we're going to FOIL out x plus h, and then distribute the 2 to the x and the h here, and distribute the negative, and what we get is this. And there we go. So you notice how we FOILed out the x plus h. That is right here. Right here is the x plus h FOILed out. And then 2x plus 2h, that's this term right here. And then, oops, I have an error right here. This should be a plus 1 right there. That's a plus 1, plus 1, plus 1. And then just distributed the negative to each term here. Now we have some cancellation here that we can do. Notice this x squared will cancel with this one. This 2x here will cancel with this one. This number 1 here will cancel with the negative 1 here. And then what we have left is that this is all equal to now we do have some further cancellation here. We have an h in each term in the top, so we can cancel an h from each term up here with the h in the bottom. So we can do this. This will cancel, leaving a 1 here. It will cancel with this one, leaving a 1 there. It will cancel with one of these h's here, and this one here, leaving a 1. And then what we have then finally as our answer is 2x plus h plus 2. And that's our final answer. So that is f of x plus h minus f of x divided by h simplified out to this. And by the way, what you've done here is if you let h equal 0, you've actually evaluated your very first derivative. This is actually the derivative of this function, and we will, well, if you haven't seen derivatives before and you don't know what it is, we'll discuss that, and obviously that's the whole point of the course, and we'll discuss that in much more detail later, so don't worry about it if you don't understand what a derivative is yet. So if you put 0 in here for h, you get 2x plus 2. That would be the derivative of this function. Alright, let's take a look at another example. So let's look at this one. Does the equation y squared equal x define y as a function of x? Well, if you think back to the function definition, for each x that we plug in here, for each number we plug in for x, I should say, we should only get one number back for y. Well, notice if we plug 4 in for x here, then we get that y squared should equal 4. So how many possible values for y will make this equation true? Well, you notice we could let y equal plus or minus 2. So we actually get back 2 values for y. Notice that when you have to remember a rule. When you have an equation like this and you take the square root of both sides, you actually have to say that y equals plus or minus the square root of 4, and that's how you get back the plus or minus 2. So you have to remember that rule when you're solving an equation like this, when you take the square root of both sides. And the reason you have to put the plus or minus here is because, well, you can see positive 2, if I put it in for y, I get back 4, And if I put negative 2 in for y, a negative number squared is a positive number. So these are both solutions to this equation. So you need the plus or minus. Well, so what we have then is we put the number 4 in for x. We do not get a single number y back. We get back two different numbers. And so this equation does not define y as a function of x. And graphically you can see that this is not going to be a function because its graph will not satisfy the vertical line test. So let's take a look at the graph. So right here is the graph of the function, or I'm sorry, it's not a function, but the graph of the equation y squared equals x. So this is what it looks like right here. So you notice we do not pass the vertical line test for this particular graph. A vertical line crosses at 2 points. So in particular with putting 4 in for x, graphically, this is what we got back, you see. So you see if we put 4 in for x here, we get back that y could be 2 or negative 2. So you get back two possible values for y. This does not define a function. You may recognize this function, this graph, I keep saying sorry, this graph is actually composed of two different functions. It's actually composed of the square root of x and negative the square root of x. The top part right here, this piece right here, is the graph of positive square root of x, and this piece down here is the negative square root of x. So when you try to solve this equation for y in terms of x, you actually get back two different functions, positive square root of x and negative square root of x. Now let's take a look at definitions for domain and range of a function. So here's a definition. If we're given a function y equals f of x, the implied domain are all the values of x for which the function can be evaluated. So that's what we call the domain of our function. It's just any number that you can plug in here for x and have this make sense. That's our domain. All those numbers are going to be our domain. The range, on the other hand, of the function are all the values y for which there exists a number x in the domain in which y equals f of x. Now let's take a look at an example here to clarify that a little bit. Let's find the domain and range of this function, the square root of x minus 2. Alright, so to find the domain for this function, if you recall that anything underneath the square root here must be positive in order to evaluate it. We're not going to consider it possible to evaluate the square root of negative numbers. Now, in reality, you can take the square root of a negative number mathematically, but it turns out then to be a complex number, if you remember anything about the number I, and we're not going to deal with complex numbers here. So we're going to pretend that you can't take the square root of a negative number. So we need to find all the x values that we can plug in here and have this make sense. Well, that means that we need x minus 2 to be bigger than or equal to 0. And then solving this equation for x, we get that x must be bigger than or equal to 2. And so if we want to write that in interval notation, then here is our domain. Our domain would be 2 to infinity, like that, with a closed bracket at the 2, because we can take the square root of 0. If we plug 2 in for x, that's okay. Square root of 0 is 0. Now, let's think about the range for this function. Down here we have the graph. Finding the range can be a little difficult at times, so we're primarily going to find the range by considering the graph of the function. Now, the domain you should think of as being residing on the x-axis. So the domain is down here. If we look at the graph of the function, notice it is only defined for x bigger than 2. And that's what we found, bigger than or equal to 2. So this is where our domain is, and it lives on the x-axis. Now the range is going to live on the y-axis somewhere. So we have to think, where are all the numbers y in which when I draw a horizontal line over, I hit the graph somewhere, which means then that there is an x value that gets mapped to that y. If you can do that, then this y right here, as I have it graphed, would be in the range. So all the numbers where we can draw a horizontal line over, hit the graph, those are going to be the numbers that comprise our range. Well, we can see from the graph of this function that all of these numbers are in the range. Or basically, our range goes from 0 all the way up to infinity. So graphically, we see that our range goes from 0 to infinity like this, and close bracket. Notice 0 is a member of the range, because if I put 2 in for x, the square root of 0 is 0. And so 0 is in the range, because 2 gets mapped to 0 under our function. F of 2 is equal to 0. So that's how we're going to deal with the range here. We're just going to look at our graphs and try to pick out the range as values along the y-axis. Now let's consider this example. We want to find the domain and range of the function f of x equals x squared plus 1. So first of all, let's think about the domain. So what are all the numbers x that we can plug in here and have this function be defined? Well, there's really no restriction on what we can plug in here for x. No matter what number we plug in here for x, we can multiply it by itself and then add 1 to it. We wouldn't be taking the square root of a negative number, or we wouldn't be dividing by 0. There's no problem putting any number in here we want for x, and so our domain is going to be all real numbers, which we can write like this. Just the open interval from negative infinity all the way up to positive infinity. Now for our range, we have to think about what the graph of this function looks like. Well, here we have the graph of the function x squared plus 1. Notice that it has a vertex at 1 on the y-axis. That's because this is simply the graph of x squared, which is your basic parabola with a vertex at 0 like this. It's just a basic parabola shifted up 1 unit. And we will talk about these shifts a little more in an upcoming video slide. Now, if we look at this graph over here, notice we have a vertex at 1 on the y-axis. All of these numbers from 1 all the way up to positive infinity are going to be in the range. For example, notice that 5 is going to be in the range, because if I go over, I will hit the graph somewhere and then drop down, so there is an x that gets mapped to the number 5. In fact, there are 2 of them. Plus and minus 2 get mapped to 5. So 5 is in the range. Notice that f of 2 equals 2 squared plus 1, and that is 5, and the same for f of negative 2. So 5 is in the range. And in fact, all of these numbers from 1 all the way up to infinity are going to be in the range. So our range goes from 1 to infinity with a closed bracket at the 1, because 1 is in the range of this function. Notice if we set 1 equal to x squared plus 1, and we try to solve that for x to prove that 1 is in the range, we get that 0 equals x squared. So x can just equal 0. So f of 0 equals 1, so 1 is in the range. Alright, so that's how we find the domain and range for this function. And finally, let's consider this example. Let's find the domain and range of this function, 1 over x squared minus 1. So for the domain for this function, well, the only thing that we cannot do here is have 0 in the denominator. So we need that x squared minus 1 cannot equal 0. As long as this holds, then that particular x value will be fine to plug into our function. So let's actually find where this is equal to 0 and then exclude those points. So if we set x squared minus 1 equal to 0, well, we simply get x squared equals 1, or x equals plus and minus the square root of 1 when we take the square root of both sides, or x equals plus and minus 1. So therefore we have to exclude these points, because if we put positive or negative 1 in here, then we'll get 1 over 0, and we can't divide by 0. So therefore our domain will be all real numbers except 1 and negative 1. So let's write that out. Now if we want to write that in interval notation, that would be equivalent to just writing and that's how we would write our domain. Notice writing it like this, the domain is from negative infinity to negative 1, excluding negative 1 because of the open parenthesis there, and then negative 1 to 1 with open parentheses, those exclude the negative 1 and 1, and then 1 to infinity with open parenthesis at the 1, that will also exclude 1 from our domain. Now the range is a bit trickier for this one. Once again, let's just look at the graph. Well, over here we have the graph of our function. Notice that we actually have what we would call vertical asymptotes at 1 and negative 1. Those are points where our graph does not exist. Our function is undefined at those numbers. Now if you look at the graph, notice how the graph, it never quite touches the x-axis as we go out in this direction and in this direction, but it does get infinitely close to it. And so all of these numbers will be in our range. We see that we can go over and we hit the graph somewhere. So it looks like our range is going to go from 0 to infinity, but it doesn't include 0 because if we go over, we never actually touch the graph. So our range is going to be 0 to infinity. And then we also have numbers down here in the range. All of these numbers are in the range. Notice if we go over, we hit the graph somewhere. And it goes all the way up to negative 1 here. That is in our range. But the numbers between 0 and negative 1 on the y-axis, these are not in the range. So these numbers here, these are not in the range. This portion is not in the range. And so the range would also include the numbers from negative 1 to negative infinity. And let's write that as close bracket at the negative 1, and then like this. So there's our range. Negative infinity to negative 1, union 0 to infinity. Close bracket at the negative 1, open bracket at the 0.